Here we are once again at the physics video lecture. This is Physics 4B video lecture 18. I had quite a few inquiries about the quizzes, a lot of questions about the homework, so we'll just spend the hour or the better part of an hour doing a review. And in particular, so the quizzes number 6 and 7, people were asking about, so I'll put those up there. The quiz coming up on Wednesday, quiz number 8, I want to talk about at length. It's based on a homework problem that we had done. So good, let's look at these quizzes. So quiz 6, there was an electric field. Let's see what we had there. Charged ball of a given mass in an electric field. So what we have is a mass and it's carrying a charge and it's subject to gravity. There is a downward electric field, but there's an upward acceleration on this. So this field here, QE, I'll talk about that in a moment. That's going to be its direction because there was an upward acceleration. So here's how we look at that. We're going back to mechanics. Net force equals mass times acceleration. We definitely have minus mg and plus QE. Okay, magnitude going up, but it's already clear that the charge is going to have to be negative because the E field was pointing down. Okay, the E field in this problem is pointing down, so the charge is going to have to be negative. I could just say that that was the magnitude there. Okay, so QE is a magnitude. But yeah, A was given, and we're trying to solve for Q. So we're going to end up with Q equals M G plus A divided by magnitude E. It's going to have the minus sign. So in order to get this one right, I think you had to have the minus sign in there as well. But yeah, it was G plus A because instead of just hovering, the homework problem had a situation where the charge was at rest. It was the same problem, charge is at rest. Here I decided to have it accelerated upward. Okay, so that would have been the difference. You had that G plus A. Good, so that was the 6th quiz. The second one was related. I think also something on the homework. So quiz 7. Here I had that picture. And we're looking at a charged mass. I'll draw this large enough here. Charged mass, gravity is pointing down here. It's deflected at an angle because there is an electric field pointing to the right like that. That's what's providing the deflection. So what was given, the mass, the angle, the electric field. And we're trying to find the charge again. Trying to find the charge. Find Q. Okay, so yeah, there's mass and charge right here. So what we're looking to do is to set this up as a mechanics type of problem. I'll draw right here. So the string has a tension mg down this way and QE in that direction. Those are the 3 forces holding this thing in equilibrium. So let's do the standard X and Y axis. And then we can say in X direction, we have minus T, this is tension, times the sine of theta, right? You would find your theta here again. So minus T sine theta plus QE is equal to 0. In the y direction, you have your T cos theta pointing up and your mg pointing down equals 0. So two equations and two unknowns. We don't want to know the tension. We want to find the charge. So that should work out right here. So the charge from the first equation is T sine theta divided by E. Okay. T sine theta divided by E, that's the charge. And then we'll take T from the, so we'll have sine theta over E. And then the T will get off the second equation, mg over cos theta. Mg over cos theta, so our answer would be mg tan theta divided by E. Good, so that was quiz 7. Now, this next problem is important. I want to talk about at some length and set up. This is problem 20, chapter 23, problem 83. So 2383. A number of people asked to have that one done, and our upcoming quiz is going to be based on this problem as well. So this is a pretty rich and interesting problem. The idea is we have a conducting sphere, radius R1, and we charge it up, and then there's a certain potential to it. So initially here, we're going to have V1 is equal to Coulomb constant Q1 over R1. And actually, how am I going to write this down? I'm just using Q, not Q1. Okay. So that's the potential it was charged up to. They gave us this number, V sub 1. And they said we connect it to a second charge, a second conducting sphere, with a long, very thin wire. And there's a bunch of physics going on here. So let's discuss this for a moment. First of all, why can I say that this is KQ over R sub 1? Back when we studied Gauss's law, we knew that outside of a spherical charge distribution, we have the same form as a point charge. So actually, outside of this charge, for lowercase r greater than R1, suppose we were out here at some distance r, okay? We would just have the potential of a point charge. We would also have the field of a point charge. So moving in from r closer and closer until we get to the surface, then that's what our potential is. Outside, it would be V KQ over R. Moving into the surface, spherically symmetric charge distribution, just like a point charge, okay? Now, why do we have to have this wire be so long and thin? It's because we now connect this sphere, and charge is going to travel along the wire and charge up the second sphere. And they have to be sufficiently far apart so that the fields don't materially affect each other. That is to say, we still want to have a spherically symmetric charge distribution. If these things were close enough together and they have the same sign of charge, of course it would push it apart, and you'd have less on one side and more on the other. Okay, so that's the reason for the long wire. The wire is thin so that a negligible amount of charge is on the wire. So after we connect these things, so this is the first part here. So initially, now after we connect them, some of this charge is going to flow to the second sphere. It'll be conserved and we'll have Q1 and Q2. So let's go ahead and kind of make a note of that. So second point, after we connect, charge Q is going to be equal to Q1 plus Q2. That is to say we'll have Q1 over here, Q2 over here, okay? But because it is conductor, conducting wire, and conductor, the entire system is now an equipotential, okay? So after we connect, we have this, and I could say, and V is equal to KQ1 over R1 equal to KQ2 over R2. I'll call this, this is equation 1, this is equation 2 here, and this will be our equation 3. So now we can make use of this. Our problem was asking us to find R sub 2. We'll just just continue with this. But yeah, right now I've just made use of the physics, right? Charge conservation, well, first of all, spherically symmetric charge distribution, form of the potential. Charge conservation, so it's distributed in the other side, negligible amount on the wire, and then equipotential surface. Therefore, we have this third equation here. Good. So let's see. Now, we've got this V1, which was given K, and then we'll have Q1 plus Q2 over R1. So just keep going with this. So we have K, Q1 over R1 plus K, Q2 over R1. Now this we already know. KQ1 over R1 is the new V. Okay, I'll just put that there. This is equal to V, the new one. This thing here, we don't quite know what it is yet, but we can multiply top and bottom by R2. That's just multiplying by 1. Now, KQ2 over R2 is again equal to V. So this whole thing here is equal to V times R2 divided by R1. So again, now what do we have? We have V1, the original voltage that it was charged up to is equal to V times 1 plus R2 divided by R1. And I could actually leave it at that, because then you can solve for R2 over R1. And yeah, the answer was given in terms of R1. So you solve for R2 over R1, and you get the answer. So yeah, the quiz number 8, I'm basing on this problem, so study it well. Like I said, there's a lot of physics here, and it's a good problem. Okay. And yeah, go back into the book if you didn't get it and see what they gave as an answer, and you'll see it's consistent with this right here. Okay, let's consult the clock. So, what is next? There were a lot of homework questions, and I'll just put a note here before I finish these, just because there's a lot of physics. First thing was potential of a point charge, right? So, potential of a spherical charge distribution potential of spherical charge distribution is the same as a point charge if you're outside that distribution. Inside this spherical charge distribution, the E field is zero, the potential is constant. Okay? But if you're outside and coming to the surface at R1 is the limit of being outside. So we had that. The second point were two things: a great separation in order that these fields don't really affect each other, and charge conservation. Charge conservation. And the third point here was that we had equipotential surface. Equipotential. So actually a lot of themes from that chapter being dealt with here. Okay, so other questions concerned the Rutherford problem. Go ahead and write that down. So this was 2325. Rutherford. And they're launching doubly charged alpha particles at gold foil. Okay. But really, I'll just draw a picture here. So we've got some 1/2 mv squared and some charge, and it's being launched at this target, which is a gold molecule, and the idea is it's energy conservation. So kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. But out at the initial point, we're so far away that there is no potential energy. Potential energy vanishes, so what we have here is initial potential energy plus 0, and then the particle actually comes here and comes to a stop at distance d. Okay. And therefore, the final kinetic energy is 0. And so there's our equation. This is actually just being given to us in terms of so and so many mega electron volts. Over here, we have, say, the Coulomb constant, the charge on the alpha particle, and then the charge on the gold foil divided by d. So principally, this is the problem. Solve for d. Now, if you have to go back and forth between units, then, for example, d is you want to end up in meters. Here they're giving us mega electron volts. We have the Coulomb constant, so it can take a bit to work around the numbers. But I'll just remind you guys, 1 electron volt right? That's a unit of energy. So that's a charge 1.6 times 10 to the minus 19 coulombs times, in fact, I'll leave the coulombs out here. I just said it, coulombs times 1 volt. But if you have coulombs times volts, that would be joules. Okay. Joules. Okay. So you can make your conversions. But yeah, that's how the Rutherford problem is set up. What next? Problem 55. A number of people wanted to see. I was wondering if I had done that before, but I'll do it again. Yeah, so this is the potential of a linear charge distribution, a wire on the x-axis. It's a good problem. Yeah, chapter 23, problem 55. If I did it before, so be it. We'll just do it again. So we're on the x-axis. So 23, 55. We're on the x-axis. We want to get, and then we're going to do a limiting case. Good. So here's x and y. We're not going to deal with y. From minus L over 2 to plus L over 2, we have a linear charge distribution. And out here at some point x, we want to know what the potential is. And then we want the case when x goes out to infinity, or when x is much larger than L. That's L, that's a 2, okay. So our potential here is K integral dq x minus x prime. Okay. And what we're doing is we're integrating our q, I'll say q prime. We're integrating from this point, it's 1 over x for every increment of charge along that length there. So when we turn this into an actual integration, we have k minus L over 2 to plus L over 2. Now the dq, it's a uniform distribution. It's going to be q divided by L times the dx prime. So that's our dq, and then we have 1 over x minus x prime. I can do away with the absolute values because I'm over here on the right side. So that would be kq over L. And then the integral 1 over x minus x prime. We're integrating with respect to x prime, so I get minus 1, and then I have the natural log of x minus x prime from minus L over 2 to plus L over 2. So I just have to evaluate this. And that'll be an exact expression minus kq divided by L, natural log, and upper minus lower boundary. So natural log x minus L over 2 divided by x plus L over 2. So there's our answer. But what we want to do next, makes this interesting, is we're going to say for L, for x greater than L, what does this turn into? Okay. Well, it's supposed to turn into kq over x. Because if you're far enough away from it, it's supposed to just look like a point, act like a point. Okay, so we can do that. Okay, we can do that by operating on this a little bit. And in fact, we'll still have an exact expression, KQ over L, if we divide top and bottom of the argument by x. So that's the natural log of 1 minus L over 2x, 1 plus L over 2x. Okay. At this point, both arguments here, or the numerator and denominator, are both dimensionless, and we can say we've got minus KQ over L, natural log 1 minus L over 2x minus natural log 1 plus L over 2x. So yeah, this is still exact, but now what we're going to do is approximate log of 1 plus a small quantity by that small quantity. Okay. So I'll just put this here. Note natural log of 1 plus a approximately equal to a when a magnitude is much less than 1. Okay. So here we go. When we do that now, so now this goes to, for x much greater than L, minus KQ over L times negative L over 2x minus L over 2x. And now it's just a question of minus signs are going to cancel, KQ over L, and we'll have 2L over 2x. 2's cancel, oh. Yeah, 2's cancel, L's cancel, KQ over X. Okay. So there you have it. Whoever wanted to see that then. Okay, then we're in this was chapter 23. So now we're in chapter 24. Actually, somebody wanted 2441. Let's go ahead and talk about it. In fact, it's good. 24, 41, and 49, they kind of go together. 41 is just some definitions. Basically, 49 also. Okay, so parallel plate capacitors, really, we're just going to, but we're going to use this in 49. So for 2441, remember we've got that parallel plate capacitor, I'll draw it. And we can have a charge plus Q and minus Q distributed uniformly on it. And there's a separation D between the plates, and there's an area A. So the capacitance, we have Q, C, D. Capacitance here, we're not using Coulomb constant, we're using epsilon naught. So C, epsilon naught A over D. And the first part of the problem, we were given C and D, so we just solved for A. Okay. What else was in the problem? And then from this here, what were we solving for? V. So then V is equal to Q over C. And they may have asked for the energy as well. Actually, that'll be good to have up on the board for what we're going to talk about. So a half CV squared, U is equal to half CV squared, or Q squared over 2C. Those are equivalent expressions. And then the field times the D is V. Okay, so anyway, for problem 41, you were just manipulating these facts. these formulas. Okay, the next problem was for a capacitor that consists of two concentric spherical conducting shells. And the interesting thing there was we wanted to bring it back to this expression right here. So let's try that. And that would have been problem 49. So 2449, we have these concentric shells here, and R1 and R2. Okay. And we're just going to take the potential as being, and I'm just going to do the magnitude here. Depends on which side the charge is on. That's what sign of charge is on what. So we'll just take that as being K integral Q over R squared dr from R1 to R2. Okay. Because what is that? That's the E field of a point charge. And say you have a charge, positive charge here and a negative charge on the outside. Actually, it doesn't matter. Either way, as soon as you're between R1 and R2, you're just looking at the field of a point charge. So we can do this. We have KQ, and then the integral of 1 over R squared is minus 1 over R. R1 to R2. So we'll have KQ 1 over R1. So I'll do the bottom limit first and get rid of the minus sign. 1 over R1 minus 1 over R2. So we have our V magnitude at least will be KQ R2 minus R1 over R1 R2. Good, so that way we kept it all positive. Didn't have to worry about sign. Yeah, now what? We want the capacitance. So, and C, capacitance, which is just Q divided by V. So Q divided by V. Well, we'll just invert this thing. We'll have KQ R2 minus R1 over R1 R2. And we see what the capacitance is. And they gave it to us in the book, right? So let's just write this down. The limiting case is kind of interesting. Yeah, we actually want to have all this stuff up here. So our capacitance, we'll just write it down right here. So I want to go back to, so 1 over K is 4 pi epsilon naught. So that's what I wanted to put here. 4 pi epsilon naught, R1, R2, R2 minus R1. Now it's always nice to recognize things in a limiting case. So what they asked us to look for was, suppose the radii are very close to each other. So let R1, so R2 is equal to R1 plus some small number D. D is much less than R1. Then the product of R1 and R2 is roughly just, so then we've got R1 approximately R2 we'll set them equal to R. And what we're going to have is 4 pi. So C is going to be approximately 4 pi epsilon naught R squared. And the R2 minus R1 is just going to be D. Okay. But this would be epsilon naught, and then 4 pi R squared is the surface area of a sphere. Okay, so we're just going to call that area, and then the separation distance D, which is what we were looking for. Okay, good. What else is on our plate? And these next several are also change of pace. Now we're talking about some basic circuits. Okay, that's important. Let's look at the clock here. Okay, there was another really interesting problem with the same spherical capacitor, in which we were going to integrate up the square of the field, E squared over epsilon naught, to get the energy density. I'm just going to recommend this one to you guys so we can move on to these circuit elements. But what number was that? Let me write that down. So that was 2450. So a note on 2450. Here, everything's still up on the board. What you do is, there's the E field, Q over R squared, KQ over R squared. You want the E field squared energy density. Remember, we had energy density, energy stored in the field, and you want to integrate that up from R1 to R2. And you want that total energy, and you're going to compare it to one of these two expressions. Yeah, you try both. So when you do that integration and get the total energy stored in the spherical shell capacitor, and you have to do an integration, but it's no harder than the one we just did, then you can take that energy and compare it to this expression here. The capacitance you're going to use is the one we just found. Okay, so actually that's a really interesting problem as well. Highly recommended. Okay, good. We're going to move on. I'll just use as here. I'll just label some of these. So we're using this star and this. Yeah. Star. Okay. So we got a couple of circuits here. And these are good. This next set here, I'm going to do something like this on next week's quiz. So definitely worth talking about. Let's go ahead and erase this. So we have some equivalent capacitances and voltage drops, and I'll look at problem, so 24, 31, and 32. 24, 31, 24, 32. And yeah, let's look at these for starters. So I'm not going to plug any numbers in. So we have 3 equal capacitors, and if we put them all in parallel, so here's A and B. Hook up a battery across A and B, and if we do 3 capacitors in parallel and they're equal, then the capacitance here is just going to be C1 plus C2 plus C3, in this case 3 times C. Okay. So it was 15, and therefore you found out that each individual one had 5. Okay. But then we had different ways of wiring this, and another way would be to do them all in series. Okay. We've got 3 capacitors in series, and now we have C equivalent is 1 C1, 1 over C2, 1 over C3. In this case, it's 3 over C. So the equivalent capacitance, not so fast. Didn't I warn you guys about that? 1 over C equivalent is 3 over C. So now the equivalent capacitance is 1/3, and that's where you had that 1.6 was 1/3 of 5, that thing right there. And then there are different ways. I'm not going to do them all. Another one is, here's point A, and then you have, okay, A and B like that. You want the equivalent capacitance here, you can do it in 2 steps. You could say 1 over, because these 2 are in series, you can say 1 over C equivalent is equal to 1 over C plus, I'm going to label them 1, 2, and 3, plus 1 over C sub 2, 3. Okay. Now you have to find what's C sub 2, 3. Okay. C sub 2, 3 here, this is 1, 2, and 3, are in parallel, so they add. So that is equal to 1 over C plus 1 over 2C. Okay. And then when you, so then you end up with 1 over C equivalent is equal to 3 halves, right? 1 plus 1/2 over C, and then you invert that and you get the C equivalent as well, so it's 2/3. Good, and then the third one is this 2 in series and 1 parallel. Okay. The other, or the 4th one. Good, so that's how these are tackled, and I'm going to go to the next problem to say something about the voltages. So problem 32. What we want to be able to do is, for some simple setup like this, given say a voltage to find and capacitance to find all the charges, find all the voltage drops on a simple configuration like this. So again, I'm not going to plug any numbers in, but for these simple objects you want to be able to tackle this. So this next one here, 32, what did we have? They gave us a voltage of 200. Okay, there's just, I'll call it delta V, say that's given. And then what do we have? Yeah. So this is C1, C2, and then we've got a third capacitor out here, C3. So you want to be able to find the equivalent capacitance. So C equivalent is equal to 1. These are in parallel, isn't it, right? In parallel. So we'll say C equivalent is equal to C12 plus C3. Okay. And then 1 over C12 is equal to 1 over C1 plus 1 over C2. So you just work through systematically. What about the potentials and the charges? Well, the potential's the same over here and here, so we can say that Q is CV, so we would have Q3 would be C3 times this V, or delta V that's been given. On the other hand, we have an equivalent capacitance here, so we can say, and Q12 is equal to C12V. So now we have those charges, but we want to get the voltage drops across these two individual capacitors. So then we would say, okay, V original delta V is equal to V1 plus V2, and then we use this equation again to get the individuals. Okay, so you just do these things systematically and step by step, and we're not going to do anything really any harder than this. I could build one of these no harder than this for the quiz, and then ask you typically write one answer, so I could say what is this delta V1 here? Is V1 as an example. Okay. Good. Okay, let's see how time's going right now. Okay, let's do a couple of circuits. People had questions on the currents as well, and then we'll wrap it up. Yeah, so chapter 25, problem 70. We'll look at that one. And again, without any numbers. Let's see what we have here. We have chapter 2570. It's a basic one. Okay, A. There's a resistor. And then we have two more, and then here's point B. So we're going to put voltage across A and B. And I think we're given VAB. Okay, so VAB is given. Okay, so first of all, we want to get a current. So I'll just kind of go through some systematically here. So R equivalent is equal to R1 plus, all this R2 and R3, plus R sub 2, 3. Okay. For equivalent resistances in series, just add. And this R sub 2, 3, we would have 1 over R sub 2, 3, 1 over R sub 2 plus 1 over R sub 3. It's just the opposite of what you have in the capacitances. Okay, so consider these known. What's next? So we want to have the current through the entire circuit. So that would be this current here, and then it splits into two currents, but then it joins up into the same current there. So that's the current through the entire system, and we use Ohm's law, so I is equal to VAB over R equivalent. So that's the current, okay? But what about the current through these individuals? Well, these two are in parallel, so we can have, I call that C. So I through R sub 2 and I through R sub 3 would be found here as well, except for the following. So I sub 2 would be V sub CB over R sub 2. We're just making repeated use of Ohm's law, but we don't know what V sub CB is yet. However, we have a voltage drop from A to C, but all right, V sub CB is equal to the original one, AB, minus the voltage drop across here, AC, and that is I times R1. Okay. So that's the new voltage drop from C to B, and then we can keep getting, we can get the currents here and so forth. And we can get the powers and everything. So a simple circuit like this we want to be able to analyze. And again, the way our tests are set up, I have you analyze something like this, and I'll ask for one of those unknowns. Okay, one of those currents, one voltage drop, that type of thing. So if you can answer every question about a circuit like this, and you can, then you'll be in good shape. Okay, let's see. Good, I think we're going to leave it at this for today. Our next chapter, if you want any more problems like this work, just let me know in the emails. Next hour we meet, we're going to talk about magnetism, so we'll be moving on into a new chapter. Okay, see you then.